So let's bring the house to order. I'm happy to introduce our plenary speaker today. It's Professor Hanseok Ko from Korea University, but he has a long connection with this place. He did his undergraduate degree at Carnegie Mellon. So those of you who are from CMU, you're a fellow alum. He has two master's degrees, one in mechanical engineering and one in electrical engineering. You might wonder why, whether it has anything to do with robotics. Maybe it does. And then a PhD, of course, in electrical engineering as well. He works on multimodal signal processing, images and speech and things like that. And other than being a professor like many other people, he actually has an interesting background. He's actually started two companies, which are now publicly listed. And I happened to see one of them before it went public, really cool interactive demos of avatar, which looks at you, understands what you're gesturing at, looks at your facial expression. Maybe he'll talk about it a little bit. And he and I, of course, go way back. Like after going to Korea University in 95, he came over for a sabbatical and he spent it here at Hopkins. And I had just joined Hopkins a couple of years before that. So we overlapped during his sabbatical year here. So without further ado, let me give you Professor Hanseok Ko. Turn on the mic. Yeah, good.
Thank you very much for a great introduction. Good morning, everybody. Good to see you here. I'm very, very happy and excited because I can remember some of the faces. I don't know if you can remember me, but I can. But anyway, I want to congratulate you because I think you are a bunch of people who were selected, right? The top 3 or 4 teams around the world, and you're here. So that's a big thing. I'm very happy and excited to share my story. By the way, this is actually a scene of the university that I belong to in Seoul, Korea, not somewhere in London or UK. It's got some Gothic building. Don't get confused. So yeah, it looks pretty very, very learning, attracting learning type of environment. Anyway, so what I like to do is sort of, Sanjeev mentioned about this robotics background that I have. It's really a convergence of the two, right? The machine and to making it intelligent, right? So I've been actually having this interest for very, very many years. And my thrust lately has been to make it much, much more closer to human-like interface. And I'm just very happy and excited, as Sanjeev mentioned, that I was able to put together into a company which became listed on NASDAQ just this year, March of this year. So I'm very happy and excited. So what I'm going to do is actually in the middle of my talk, I'm going to share some of the videos that sort of mimics what I have in mind as far as the concept of this interface. Anyway, so this is sort of like the outline of what I like to talk about. So I'm going to just give you a brief overview of the progress of this interactive HMI, which is actually my own story of my career, my journey in academia as well as research. And then I'm going to share with you of how or what I think would be a good thing, good approach to make it as interactive as possible for the machine in terms of the pipeline. So these are some of the very important components that would be very, very useful and also important to make it all go in this cycle. So I'm going to share with that. And also some of my current research topics. And I think a lot of you attending this workshop are probably doing the same thing. There's going to be a considerable overlap. So, I'm very, welcome to your suggestions and whatnot for a possible work together. Okay, so actually, I'd like to go back to a little bit of a history dating back to 2013, right? So that's ICASP in Vancouver. So what happened in ICASP Vancouver 2013 is that, right, Jeff Hinton stood up as the plenary speaker And that's where I think he, first time in a very large conference, shared, right, his success story about applying DNN to speech recognition. And that's when I think with ICASS, having so many attendees at the time, Vancouver is also a very, very famous place, right? I went there. Actually, I went there for two reasons, to actually hear from Jeff Hinton, and also at the same time to bid for hosting ICASS in Seoul, Korea in 2018. So 5 years down the road. But anyway, I think everybody was so excited and happy to hear, right, a story from Jeff Hinton of his making this very, very successful demo, as well as applying DNN to speech recognition. So I think that's when there has been a lot of work in DNN, similar architectures and so forth. But myself, for example, when I did my PhD, it was about artificial neural net, right, in the 90s. But this artificial neural net also had, as you might have heard, gone through a lot of this winter, okay, because of the lack of good computation power and so forth. And what I did for my PhD was actually to design artificial neural net, which what we call as autoencoder architecture. Back then, I called it as an associative memory. Have you ever heard of associative memory? Really? Okay, excellent. Okay, I thought everybody probably forgets about associative memory. But anyway, I came up with that, I coined that term there, and I did a lot of work. But then again, with the computation problem and so forth, I sort of, put it back behind me and did other things like HMM, all these signal processing, stochastic related work, aside from not really delving into artificial neural net anymore. So this was actually an eye-opener to me, Jeff Hinton, in 2013 at the conference in Vancouver. So I think that's when I realized that everybody probably also felt the same way, right? They probably said, wow, this really works, right? And I think that's when everybody sort of began looking into, people in our sort of community, into that much, much more deeper. And soon, right, the next year, the following year, 2014, Goodfellow came out with GAN, right? And a couple of years later, guess what? Transformer, right? 2017. So a sequence of these really big events just were taking place.
I can get rid of that the bar. So let's do the same thing.
Oh, okay.
First of all, let's say yes to this. Let's say something. Say okay.
Yeah.
And here we go. We need to hide this stuff. Was it this one?
Yep, that's it.
Okay. Does that take care of it, Brian? Yeah. What is this? Is this part of the slide? Okay.
No. It's somehow it's still there.
Oh, wait, it's going. Yeah.
Oh, okay, it's disappearing. Okay, great.
Thank you.
So my laptop is alive, right? Okay.
What did it say? I don't know what it said.
It says that the application, the shared window is where it should be moved at, not with my computer here. All right, let me.
Instead of just sharing the PowerPoint window, is it possible to share the entire screen?
Yeah, sure. That's.
Let's try that maybe.
Okay.
Exit your presentation. Just go ahead, Brian.
Should I exit it?
Yeah.
I'm gonna try to see if this computer looks okay.
Okay, so I'm gonna, yeah,
And then let's try to, yeah, I'm trying to figure out where the bar went. Do we actually? We'll share the entire.
yeah,
Uh,
yeah, that's it.
that's-
Mhm.
And then which one? Which one's the linkage? Okay.
Does that work?
Yeah. The bar. Why the bar is added? This one, right?
Yep. Uh-huh.
And whenever there's something popping up, it will block it for a second, but it will go away.
Okay, okay, good.
Okay.
All right, so let me continue. A little bit of a technical problem here. So just one year after, right? 2018 Calgary, we have another ICAS, and that's when Jan LeCun was invited to be the one of the plenary speaker. And of course, I mean, he is credited as inventor of CNN back in the 80s. But I was, very thankful for him coming and sharing his stories about some of the limitations of CNN in 2018. So you see the sequence that I'm talking about now is that 5 years from 2013, we have had 2018, and I played as the co-general chair organizing that conference. And then 5 years from there, right, 2018 plus 5, or actually plus 6, right? Because we had to bid another time because of the fact that the ICAS never took place in South Korea. So it was actually my deep heart, wanting to host ICAS in South Korea. So I bid for that again for 2024, which happens to be this year. So April of this year, we hosted ICAS 2024 in South Korea. So as you can see, 5 years from down the road, from 2018, or 6 years down the road, I wanted someone who is very, very, an epic model of someone in AI to also be a plenary speaker. And I was actually hoping someone from CLSP to come and be the plenary speaker. But at the same time, I also asked people from OpenAI. And that's when I think they were having some sort of a leadership problem. They were sort of like a little bit of an issue. So they couldn't actually come. So hopefully that maybe next year or years after, very soon, right? Someone from CLSP will come becoming that epic role model. Okay, so I was just trying to share that the ICAS has a lot to do with it, or vice versa, right? Now, in terms of this HMI, moving forward, I think there's been a great contribution done by, especially the transformer that just came. So before there was actually, I should say, deep learning and then transformer. But the future that I'm thinking of with this HMI to take hold is that it's going to play a great role being a champion, right? Merging the two parties together, right? The virtual world to that of the real world. And this convergence was to take place with a lot of, expectations and so forth, that if also people at Facebook were thinking so much about this. So they changed their name to Meta, right? So this is Meta verse, or Meta is the name. And there's also companies like movies like her, a lot of these things that were just coming to represent what real holds for the future. And I think with the 6G and AI altogether, combined all together, I was expecting a great, explosion of this revolution in this IT arena. And I think that's going to be, again, I was trying to show the first slide, a big engine for the economy to move on. Now, in terms of the background, right, of the deep learning models, we are sort of seeing this type of trend, right, from that of the artificial neural net model to LSTM. And lately, right, it's the generative AI, which is powered by transformer, where transformer is considered, right, as a type of deep learning. And transformer in turn, right, became a big engine for the large language model. So we are seeing these kinds of trends and a lot of fast movement in terms of research, in terms of activities, in terms of some of the product that's turning out. And I think we should also be very thankful to people at OpenAI because of the introduction of ChatGPT. And it was introduced to us not too long ago. And there, right, as you all know, the real power happens to be from that of the multi-head attention mechanism, right, which is embedded within the transformer. And I think everybody's amazed, including those people at OpenAI, that somehow this contextual mapping and using this inference process, that somehow it worked, right? This contextual understanding seems to work. And I think so far, I haven't really heard anybody of how it's actually working, but it seems to work, right? It seems to work. But I think that's a discovery that we need, because we need to make this progress in terms of AI, how we could actually make this thing become impactful to humanity, right? So this is a transformer for applied to large language model introduced by ChatGPT. And as you can see, it's essentially a mapping of each of the words, right, against any, the other words within the sentence. So it really forms some sort of a weightings assigned between each word to the surrounding words within the sentence. So with that architecture, with that format, the contextual information became mapped. And again, with this, for some reason, large language model works, right? As if it's like a magic. Of course, I mean, there's a bit of supervised learning after that, and a bit of reinforcement learning, which was introduced again by the folks at OpenAI. Now, I need to go back to the history of my own career in terms of my own work in HMI. Again, it's rooted down to robotics, which is actually a hardware. And this is where all my focus has been, is to how do you make it better in terms of interfacing between human and machine. In this case, that would be that of the robot. So let me show you a video of what this work happened back in about 10 years ago. This is 2014. Anyway, it sounds a little too loud, so I'm going to just see if I can. No. Is that okay? I mean, I'm going to just let me see. Okay, so sorry about this loud sound, but the scenario that you're seeing here is obviously in an indoor space, and there's a robot, and we have three people there, three students of mine, having an interaction with the robot. And essentially, the students are asking where a certain place is. And as you can see, you know, that within indoor space like this, there's a lot of reverberation. The floor is pretty, as you can see, shiny, as well as probably the wall and the ceiling as well. So there's a lot of reverberation. But still at the same time, right, the robot was able to see the direction of where the sound is coming from, right? The spoken language from human. And then, you know, they were able to, the robot and the students were able to interact. There is a camera that's actually there, but camera is not really doing, injecting any type of information, except that it's just trying to capture the direction of which direction the robot is actually seeing. And the top left here is that environment, right? That indoor environment. On the right-hand side is the display, okay? So this was what I had worked on with my students, working on, you know, as you can see, all kinds of signal processing type of challenges at the time. But also my aim was to make it, how do we make the robot interact with human as naturally as possible? So what do you mean by interacting with robot or having the robot interacting with human as much as naturally as possible? These are some of the capabilities I was thinking for the robot to that it should be able to handle. For example, you should be able to recognize who the robot is talking. Is this person male or female, gender, out of, let's say, 3 different people, which person am I talking to? Who is this intended person? And what's the emotional state, right? Because, you know, this is all done right now at this time, was all done just purely audio. But if we also merge that of the camera, plugged in together, performing emotional state, then it should be multimodal, right? Work together. So there's a selective attention. Who's, you know, what is it saying? And then, of course, I mean, the robot needs to be able to respond, right, appropriately. And that could also be a gesture response as well, along with the facial expressions. So these are the kind of things that I was thinking back then, about 10 years ago, that we should put together and make it a little bit more improved, right? To make it interactive. Only problem was that because it's on hardware, right? Hardware. So what happens with the hardware? Hardware, they break down, okay? Especially these components, these parts are very, very hard to get. So what happened was that it actually delayed my research progress a lot. So I decided, I was thinking a couple of nights with a deep thought, and thought maybe, what if we make the entire hardware robot into software robot? Okay, software robot. So that software robot concept is the avatar. Now, before doing that, of course, we need to have that very important component within the robot or whoever this interface is, that it has to have this ability to have this common sense dialogue, right? Common sense dialogue. And this is when, of course, we need to some means of performing contextual understanding. So here, as you can see, is a situation where common sense dialogue is very, very you know, easy for human to do, but for a machine, it was not really possible at the time. This was, again, about 10 years ago. So as you can see, at a different situation, right, the word milk would mean differently, right, in a different environment setting. Now, thankfully, right, the transformer was introduced, right, and the large language model worked. So now, that's very, very possible. As a matter of fact, transformer empowered in many different areas, especially more, I think so, in signal processing. And this was, of course, as you can see, has been applied to images for image classification, dividing the images into different patches, and not only looking at the features, the way how CNN would look, but we can also see the relationship among different patches. right? This is the power of transformer. And here on the right-hand side, you can see the result of comparison of in terms of accuracy between transformer performance versus that of the CNN performance. And as you can see, the accuracy is drastically improved. We also have been applying similar transformer type of feature extraction into audio and also speech, as well as audio being not just any regular sound, but also those of the animal species, the sound of the animal species. I've been also using this type of transformer as a means of capturing the features there. Very, very effective. So with the transformer at handy and also OpenAI, right, introducing large language model as its trained form of contextual understanding, I began thinking about building this human-like AI. Now, this is actually a structure that I was thinking, making a complete loop from that of the perception, understanding, and response. Perception, understanding, response. So I think you understand what I mean, right? Perceiving the world from the point of view of this robot or this AI, right? In terms of the dialogue, who said this and what was the emotional state? Was there some sort of gesture? These kinds of things. So avatar or the robot needs to perceive the world, and then it has to engage in dialogue, okay? And the way to engage in dialogue is, of course, to have a full understanding of what was actually intended in terms of communication, the intended communication. So understanding is where the NLP is going to become a very, very pivotal role there. And then after that, after having a full understanding of the intention by from the say human, this avatar needs to respond, right? And that response could be in terms of again, some sort of having a dialogue, but also in terms of gesture like this, in terms of like head motion, facial expression, in terms of some sort of in some sort of an emotional expression, right? Like you could have, for example, avatar scream as a result of response, right? So these are the kind of things that would make avatar becoming like that of human. And so this is sort of the first work. Again, if you can see the year 2020, this is roughly about 4 or 5 years ago. And this was my concept of trying to mimic the real human, I'm sorry, real robot using a software version. So this is the software version of the hardware robot.
There, you see that will that control your volume? Yeah, maybe you can put that.
Hello.
Okay, the sounds is a little better now, I think.
Yeah, no, you muted it actually.
Happy to see you. I'm Bubba. Do you know what kind of animal I am?
Are you a tiger?
I don't think so.
Are you a spider?
I don't think so.
I think you're a panda.
Yes, you're right. I'm a panda. What kind of animal are you?
I'm a human.
Human? What's a human? Is it yummy? Can I eat it?
But I can go on playing the video, but I just want you to know that now, so we have an avatar, right? Avatar having 2 sensors, essentially. So the sensors are actually placed up here. One is camera, and second is an array of microphone. So combination of the two playing just like human, right? The eye vision and as well as the listening, the hearing with like ears. It could pick up the direction of the sound source, and also it could, with the vision, the images, right? It could overlay, in terms of how many people are within the field of view, and sort of track this person, and also engage in dialogue. And you might have seen, right, if you can remember, that the avatar was also like waving hand, giving fives and so forth. So these are the gesture responses, which all I consider as the response. Remember the three categories: perception, understanding, and response. So these belong to all the responses, which also, again, are going to be would be very, very important to make this avatar robot as much as human, is that it has to mimic just like human. So let me just play maybe a couple, 10 more seconds.
No, you can't.
I'm just kidding. Hey, do you know what this is?
It's a ring.
So can you imagine in some sort of an educational, kindergarten, how much of an attractive, this could be for little kids? But older version, as you can see, has a lot of, it's pretty pathetic,
Well, look here.
a lot of delays, as you can
Look
see.
here. All right. Well, hello.
Yeah.
Hi, can you
So
come over here?
it does respond, but again, with, considerable delay. Here's another example. Now, this is slightly different. So the video that you just saw had the avatar pretty much independent. Here, we have another avatar, but this avatar is actually tracking the motion of a real human. In other words, the avatar is being captured, the human motion is being captured by a camera, and then the avatar sort of wears the mask of what's been captured by the camera. So it sort of like tracks. But within, so let me just show you.
Some juice. Which color juice do you want to make? So you want to make your favorite orange juice?
Yes.
Okay, what are you gonna put inside? Orange, let's go.
So there are a lot of software products now, right, that captures the motion of a person's like motion, facial expression. So we did this again back at 2019, 2020. And this was an example. As you can see, this child was just so captivated by this avatar, right? So if you want to have your a child learning something, this would be a great example, a great way of doing this, because it would completely captivate the audience there.
Some juice.
So again, just delving into the components that I just mentioned, right? The perception, understanding, and response. Within each of these big components, we have a lot different modules that are associated. And I think, again, all of these modules are, certain overlaps with, your work here that's going on. Again, in the perception mode, primary source of information would be audio and speech, but also there's vision with camera, and also multimodal, right? You need to like combine the two things. So I'm going to also show you a bit of an example of a multimodal for capturing the emotion or state of a person. And then it goes through the understanding part. That's where the NLP plays the major role. And here again, we've been very, very happy and excited with the introduction of the large language model there. So we've been sort of applying that, and as well as the responses, right? All these gestures, the facial motions, avatar generations, so forth. Just tons of these modules, very, very complex, and they need to be all integrated into one to make it all work, right? So this was a pretty challenging task for me, but we were able to actually produce a working model, or a couple of working models, so we're very happy. So here, I just wanted to quickly go through these different components, the perception, understanding, and responses, and how much the power of transformer has empowered them. And as you can see, we're sort of seeing the trend, right, in terms of ASR, right, from HMM, the HDK to, CALD to now, right, DNN-based N210, right? So it's like anybody who has the data set could do this, right? So it's an amazing world. There's also like signal enhancement applications using transformer. And here's an example of multimodal emotion recognition. Again, the model here all again contains transformer here and there. Here's transformer here, another transformer here, transformer with 3 different inputs, right? Audio, text, and video. The text is, of course, done by ASR first, and the text goes in. Audio is just purely the sound. Okay, purely the sound, looking sort of analyzing the sound of this spoken language. So this is the result, and the result should say, which is what we anticipate, that by merging all these 3 different feature sources, the recognition rate is much, much better and improved. Here, let me just play a video of this person. He's just showing his emotion facially, but he's going to also speak.
아, 진짜 짜증난다.
So in Korean, what he
진짜
says
짜증난다.
is he's actually pretty feels pretty miserable. is what
아,
he
진짜
said.
짜증나게 굴지 마.
So he's so out of the 7 different
모든
categories
서울의 날씨 좀
of
알려줘.
emotion, this is the one in the middle. He's never happy, right? So this is like combination
뭐라고?
of the facial expression and also his voice, the speech.
아,
So here's another example. So we played the same thing, applied the same thing to video of drama. I don't know if you guys ever watch Korean drama, but Korean dramas, the people there, the actors, always shout. They're very emotional all the time.
혼자 애를 낳아? 미혼모가 되게 되는 거야?
엄마 그게
혼자 애 키우는 게 얼마나 힘든데
Couple of people
미쳤어,
engaging
얘가.
in some
나도
dialogue.
너 혼자 키워서
And as you
미혼모들
can
보면
see,
짠하고 마음 아파. 근데
There's
사람들이
no bar
사정이 있겠지.
raised here,
이해해주지
right? The
않아.
happiness.
혼자 애 키우는 여자 콩나물값만 깎아도 억세다, 패자산업다.
Okay, so anybody Korean here at all? No? Okay. All right. All right. Well, I mean, there's a translate. You're going to develop something, right? Real-time translation. So anyway, so moving to so from now perception to understanding, right? This is a very typical NLP model, and now, of course, we plug in this transform-based LLM in the middle to make it all work in terms of the contextual understanding. There's also a retrieval database and analysis taking place. Also, short-term, long-term memory also needs to be placed there. Now, I'm going to go back to the understanding part a little bit later on, but now response, right? Response, again, taking the forms, much, much improved because of the transformers presence there. Voice conversion, text-to-speech, speech-to lip sync, and speech-to, so these are all now moving along in terms of making it improved. Here's an example of 3D pose estimation. This is like the motion tracking, where once you capture all the features for the motion tracking, you can then apply it to make the avatar work exactly mimicking the same way. So this is the one that was produced by my lab in the middle, and this is the one with Google. So this is the kind of features that we would capture for, again, estimating what needs to be in place for applying the avatar. Here's an example of tunified face, because the avatar that we have in mind should be very, very, it has to be 3D, first of all. So if someone gives you a picture, 2D image of a face, this system needs to be able to reproduce into 3D in any angle or direction, right? And also into like a tunified version, right? I think you've seen similar models before. So we also worked on these kinds of tunified face as part of the response category.
In those images, the three on the left were real photos?
You
were just rotating the one that was third from the left, and so I wasn't sure.
Third from the left. This one here?
Well, the one under it, in your rotation,
you're
rotating that way, so is that real?
Well, no, these are all, I think, reproduced, the 2D version. So this is slightly less. Well, it looks like the picture on the right-hand side is the truly 25 version. What we were trying to show is that these are the two pictures that were fed in. Right. So this one are sort of like intermediate stage.
Yeah.
Okay.
The third column is the 3D model, and the fourth column is the
Right. Yeah. And but also at the same time, these the pictures here also might not be the real images of the real people too, right? I mean, there are plenty of images here and there. So we were just tapping those database, right? Okay, so again, the progress of AI or interactive HMI, I think has been drastically changed because of the presence of transformer. So I sort of am using here as the tipping point, before and after transformer, right? So there's a before and after maybe deep learning, but also before and after transformer. And here we're in this, here, these are some of the products that we are seeing nowadays. So there's GPT-4 now, or I'm sure there's going to be GPT-5 coming up very soon, and different companies will produce their own products very, very soon. Now, in terms of what I consider as the Gen AI, I am going to sort of place them to the category of all the responses. Okay, remember the perception, understanding, and response. So I'm going to push everything that's on the right side of in the cycle to be part of the response as the generative AI. Now, if you delve into the text-to-speech, TTS, this is a typical model of a TTS these days, right? So you feed in text, and then what you get output would be some spoken voice, right? So here, when you go through the process, first of all, the sequence of the words become analyzed, and then they produce a sequence of the phonemes, and then you have this encoder-decoder type of setup for acoustic model generation. And the vocoder is the one that actually produces the sound from that of the spectrogram, right? So this is sort of a typical flow diagram of what TTS would look like. Now, in terms of the TTS model also, there has been a lot of changes and a lot of development and improvement because of the transformer again. So again, using transformers introduction in 2017, up until then, I think we've been sort of delving into like LSTM or RNN-based TTS, but we are seeing, right, transformer-based TTS since starting 2019, and also GAN-based TTS, and also LLM-based TTS. Now, the LLM-based TTS is like replacing the transformer with a little bit bigger model is what should be considered, right? And then here, just very recently, there's also LLM-based TTS, where the LLM-based TTS performs a style control, right? So this was, sort of was introduced not too long ago. In the middle, there's also diffusion-based TTS. So diffusion-based, transformer has been introduced, and I think everybody's really interested in that. Only thing that when we try to apply this to TTS, it just takes up a lot of time for because of this update or recurrent model scheme. There has been actually a claim by OpenAI that they solved this problem and still using diffusion-based TTS, and they also actually demoed this thing in front of us, right? But they don't really open exactly how it was done. So that's actually a little bit of a mystery to me. So we've been sort of working, delving into see if that's going to be actually a great way of doing this. So here, I'm just showing you the same things that here, the sequence-to-sequence model using LSTM. In the middle is the transformer, which is the one that we're delving in most. The one that's actually very popular is fast speech, and also LLM based, right? And so there's a GAN based and diffusion based, and again, the LLM based, the one on the right hand side, is the one with now injecting features based on the natural language, based on natural language. So natural language description of how the sound should be. Now, when I say the sound, how the sound should be, I mean, if you want to make the voice to be as natural as possible, like in the form of, like a dialogue, human dialogue, right? The tone is actually very different than when TTS is used for reading a material. Okay, reading versus in a dialogue is completely different. So we wanted to actually make from the monotonic, TTS type of spoken speech to a little bit more like dialogue style. And we are also trying to use the LLM base to be able to solve that problem. So these are some of the work that my lab and my students are involved. So first, the LLM on NLP aspect, the understanding aspect. So there's a fine-tuning also. I mean, everybody wants to fine-tune the large language model. So we also were doing a bit of that, and also augmented memory. The second research topic is to inject information fusion so that the large language model could also produce the better result, the better in terms of narrower domain, so that the responses become very much appropriate. And similarly, image to text. And fourth is the target speaker extraction. And the last one is the natural style adaptation of TTS using LLM. So again, the first 1 to 5 is all spread here between perception to response. So the first one here is a way of, well, actually we have two objectives here. One is to do fine-tuning, and the second is to inject long-term memory, okay? Everybody has their own reason for fine-tuning the large language model. I mean, large language model is just too bulky. We want to like confine it to make it, and still as powerful as the large language model. So everybody wants to make it as small as possible, and by going through the fine-tuning process. So one very typical one, very popular one is to in place an adapter, right? In place an adapter. So we've been working on this, adding this adapter, LoRa adapter, and have the large language model freeze and just have the adapter be trained by going through the fine-tuning process. So this is one thing that we did. And the second thing in terms of, again, in placing long-term memory is either a parametric method or non-parametric. So this is the result of the adding adapter. So multitask adapter versus the single task adapter is much better. And here at the bottom, it shows that this model model editor works as a part of the hyper network. So in this long, again, a cycle of training where the original LLM actually is left as is, but just training this model editor, we were able to actually do and perform what we consider as the long-term memory. We could also, of course, do the entire retraining of the large language model as well, or fine-tune it so that the domain becomes much suitable for a specific application. But there are many different ways. So this is one of the ways that we are looking into. Second is injecting contextual information into large language model. So this is sort of when you have your mobile phone, and mobile phone contains a lot of these information, contextual information that could be very useful So we merge that with the metadata, and then try to again provide much more domain-dependent information to the large language model for better responses. So this is an example of such a result. So with such a contextual information provided, this is without the contextual information provided. So these are the responses by the large language model when, for example, here, you're provided with this sensor fusion information. So much, much better. So this is one way that we could also have the large language model work for, again, making a very intelligent mobile phone. Third is the image to text generation. So this is, again, another way of making large language model respond better. So this is a situation where you have the kiosk here. And what we like to have the kiosk do is to recognize which person that the kiosk should pay the attention to, as well as what does this person do? Is this person holding a cup? If that's the case, then kiosk should be able to respond better, right? Instead of just saying hello, very mundane hello, the kiosk could say, right? How did you like your coffee or something like that? Much, much better, high quality response. So we were trying to come out with the image to text generation process before to have that sent to the large language model. So first thing that we did was to essentially detect the gazing angle of the individual, see who is the person that the kiosk should pay attention to, and also at the same time, what is it doing? What is this person doing? We want to map that action, that motion by means of the scene graph generation and feed that into the large language model. So this is sort of like the response on the right-hand side, which is being expected. So here's an example of some vision work. So if you have the bounding box in place with red, that's the person that you should pay attention to. So this is an example. I think I'm sort of like running out of time, so I'm going to just pass a little quick. And this is the target speaker extraction, right? So the idea here is that if you are driving on a vehicle, through, say, McDonald's drive-through, and you want to order something, but another passenger wants something else while you're speaking. So we want the target speaker extraction type of process to take place first, so that it can figure out and making sure to align, right, who's speaking what. Okay, so this is that situation. So we didn't use the transformer here, the old DPRNN, but we're going to also translate this into using transformer later on. So that's what this is. So this is an example of the result.
Hello, Sky. Can I place an order? I'm planning to eat the bulgogi burger set. What would you like to order? I'm not sure if I'm feeling hungry. Maybe I'll just get some fries.
So as you can see, there's an overlap of two individuals talking to each other in the midst of a very, very noisy environment, right? And so this is the result. So the mixture is there.
They
What
hiked
did
up
you
the
do
mountain,
after
admiring the
school?
breathtaking.
Right, and then so this is after the target speaker extraction is performed.
What did you do after school?
Yeah, so it works pretty well, essentially. And last is on the TTS. So there are many different goals that we want to do, but the TTS that I have now that my students are working on are two issues. One is, again, to make the TTS sound much, much more like natural. Because when you have like TTS sound, right, TTS sound becomes very, very much like monotonous. instead of having a lot of variations in the pitch and so forth. It sounds very much as if a person is like reading a book. For example, so this is the example of a human voice.
I knowed what it'd like to be the object of Master's predilection.
Okay, so this is the real human voice, and this is the TTS voice, which sounds very much monotonous.
I knowed what it liked to be the object of Master's predilections and
Can you tell the difference, right? Can you tell so we want to make this in place some emphasis so that it becomes as if that this is actually human sound. So what we are looking at are three different type of features: the pitch, duration, and also the size of the energy, right? So such information can be captured, right? And here is an example of when you go through the analysis, the size of the pitch difference for human being is much greater compared to that of the TTS. So what we did was to in place this emphasis predictor on top of, let's say, fast speech is the model that we used for TTS. So we in place this emphasis predictor and let it go through the training process. And we have to do this again for three different components, right? Pitch, the duration, as well as energy. So we just did the pitch for now. And I think it's doing some good result. So again.
Mosques, however, will still be open.
Okay, well, yeah, so this is the one that, at least if you can see the pitch differences of the result with the emphasis versus without the emphasis, you can see that you have much bigger numbers down at the bottom. So that's the result. Another one that I wanted to also see is the power of pre-trained large language model. So here we are replacing, right, pre-trained model, the LLM, for the transformer and see if it did any good. So here's a result with the pre-trained model.
Pick
LLM.
that cotton. Move along now here.
So I think there is slight improvement, but not much. So transform with maybe 8 different stacks versus very large language model, multiple transformers there. The difference, the gain has not been as much. Okay, the last one is with the TTS, but also at the same time, the focus here is on adaptation, right? If you have TTS, and if you want to add another person as part of the speaker for TTS, how much of a data do you need, right? Is it, do you need, would 5 minutes do a good job versus say 10 minutes, or should it be like 20 hours? So what we did was actually we in place the adapter, residual adapter everywhere in between. So whenever there is an addition of another speaker, we just use this adapter to perform as an additional person. So this is a result where if you have a new speaker going through this adaptation process, the result came up pretty good. So here's the result in terms of the table. I don't want to actually have you go through the listening. Let me just tell you that 5 minutes versus that of the 10-minute, no difference, so it was good. So adaptation to me actually seems to work quite well. The future work has to do with style changes by a large language model, where the large language model, as is being indicated somewhere here, says that we want to actually use the natural language to describe how the sound of this TTS should be, and that natural language could be also fed into the encoder and decoder scheme, and see if it's going to work. Actually, there's a couple of papers in that area, so we want to try that out. So far, we did try a little bit, didn't really work well, but I think that could be another way to improve the TTS. Anyway, so again, this, I want to wrap up my talk. So this was an opportunity for me to sort of share my stories, my career, my journey in interactive HMM or HMI. And for being able to do so, I also sort of shared my way of composing this human-like AI in terms of the pipeline composed of perception, understanding, response. And then I also shared some of the research topics that my students, myself, are working on. Of course, I mean, these are some of the opportunities, not only limited to these things. We have like a lot more students working on, a lot of more researchers to work on this. There's just plenty of work that can be done, especially with the large language model being available to us, as well as transformer. So I think maybe there could be another couple more years to go until maybe there's another type of transformer, big epic model that's going to also come and change the entire world again. So until then, I think I will continue to be excited. Okay. Well, thank you very much for your time.
Thank you.
And
yeah. We have a few minutes for questions. If anybody wants to ask, please raise your hand. I'll pass the mic to you. Okay. Arun back there. There you go.
Okay, thank you very much for your talk. It was really interesting. I was kind of curious to know your opinion about end-to-end language model that can deal with speech and produces speech. Because when we look at all of your tasks that you are trying to solve with your team, and the result that have been shown with a speech LLM, maybe this is something that could be interesting for you to explore. And I was kind of curious to know if you were looking at it or not.
I think
when I say speech LLM, is really like you take discrete units and then you produce also speech discrete units.
Oh, you mean the last one?
Yeah.
Like this one here? Like in terms of TTS or other?
Oh, in terms like so you have a language model like a decoder language model,
yeah,
and you take like speech through discrete units,
right.
And the model tries to learn to produce the discrete unit as well. So the model is capable basically to deal with speech and produce speech at the same time, and you can you can do whatever you want with it. But it's kind of recent.
Okay, so you're talking about speech recognition or TTS?
No, everything.
Everything, yeah. As I just am trying to show here, that I think we are still investigating.
Okay.
I think there could be. I mean, we did some work and applied a little bit. It has not been as good, but I think there's going to be a room full of opportunities there. Yeah. So large language model to be is, again, a very exciting field to get in. I think there's a chance that everything can be improved. Yes.
Any more? Kevin, all right.
Hi. So you mentioned that in the beginning you had these physical robots, and then later you moved to having an avatar on the screen, right?
Yes.
I'm wondering from the human user's side, how is it different for the user to interact with like a physical robot versus an avatar? Are there studies on how do humans behave differently depending on the kind of device
okay, so my interest was actually purely technically, how do we do this interaction, right? How do you use this the sensors, microphone, and a camera as a means for performing this interaction, but not the psychological aspect or the social aspect. So yeah, I mean, if I had more time, I could have done that. But right now, quickly, what I've done was actually move the same system, put that into a working model as an interface on a mobile phone, okay, mobile phone or laptop. So what I like to do is maybe do a live interaction with the avatar. Okay, what do you think? All right, to answer your question.
Okay, sure.
All right, so here, I think at the last page, there's a link, and I hope it's going to come up with an avatar.
Hello, my name is Sandy. I'm here to provide you with support and assistance regarding any inquiries you may have about Ozempic.
Hi, Sandy. Good morning.
Good morning. I'm here to help you with any questions about Ozempic while remaining focused on that topic.
Yeah, so I'm here at the Johns Hopkins University. Do you know anything about Johns Hopkins University? I'm asking a very wrong question.
While I'm aware of Ozempic and its use for treating diabetes type 2, I don't have specific information about Johns Hopkins University. However, I can help you with any questions related to your medication.
But didn't Ozempic come from Johns Hopkins Hospital?
While Johns Hopkins Hospital is known for its research and innovation, Ozempic was developed by Novo Nordisk, a pharmaceutical company, and not directly associated with Johns Hopkins University.
Okay, if that's the case, never mind. Goodbye.
Goodbye, and remember that I'm here to help with any questions about Ozempic.
So now this avatar has been very much trained narrowly to a particular domain, right? Because especially for healthcare type of business, we want to be, because it's being restricted, right? So to answer your question, how do you deal with interacting with such an avatar? What's the sort of like the boundary? We are always working on that problem because it really is, it actually affects to the impact, how many people could actually use this. So there are different types of use cases. The one that I'm showing you is like Ozempic for healthcare. There's also, if you can imagine, like thousands of different type of user cases, right? Like customer assistance to, like in school, right? In universities like this. Can you imagine that you will have your own teaching assistant for each of the classes you attend? Which I've done that, by the way, a couple of semesters ago. So that era is coming, okay? That you're going to have a TA just like this, and you can ask questions, and then it will, respond with good answers.
Any more? No, looks like Paula is thinking of a question. Okay, after that, Marek has one.
Oh, Marek, can you go first?
Yeah, I can go.
Because,
I was wondering, what are the hardware actually needs for such an avatar to run? Is it something that can be run on a single GPU, let's say, or when you build these large architectures? I mean,
yeah. So I mean, you're talking about training versus like inference.
Inference,
So
okay, yeah.
inference is much smaller, but still, if we have the server next to me, it's going to be more, we can save some latency time. But right now, the way this guy is running is by means of the cloud server. So there's a bit of a delay.
But anyhow, we still need some powerful hardware, I guess.
Well, not really. I mean, not really big. No, it doesn't have to be as big.
Meaning like mostly the memory is the issue. So whether
It really
let's
depends
say,
on how many people are going to be using at the same time. Scaling problem. Right?
yeah,
But if
also,
one person is using, not much of a hardware required.
okay, so like one, because I'm thinking about the models. You said you were showing you are mixing like 3 different transformers inside of the architecture. if I'm correct, for the audio, text, and video, let's
so
say.
different sources, the audio, text. Yeah, you're right. So if you can sort of think of the number of transformers per AI source, I think you can sort of like imagine how many, what would be the
Well, I would
required
imagine I would
hardware
need at least like 2 GPUs to run the inference on this or something like that. Or
yeah.
or even more, right?
Yeah, maybe A100. Yeah, that would be sufficient, I think.
So there is no like current effort to streamline this somehow, optimize it for faster inference. Is this like
There's
ongoing
always
work
need
or?
for optimization? Yes, right. It's just that I'm not in that field, so like it's
Okay.
really hard to imagine. But yeah, I mean, hardware issues is a big, especially again because the scaling, right? Not just serving one person at a time, but thousands and millions of people all at the same time. That's going to create scaling problem.
Yeah, thanks.
So the avatar in the end, and I love the panda, by the way. I really loved it. Yeah, but the avatar in the end, does it sound a little bit robotic? And
Right.
yeah,
So that's why we need to improve on the TTS side, right?
yeah,
To make it more natural, right?
yeah.
Yeah, so that's why, yeah, a lot of people there at my lab, as well as the company there, are working on that issue.
Yeah, for the panda, I think it's okay because pandas should always be like excited, right?
Right. Yeah.
But yeah, for the last one, I still there's like a lot of room to improve all of this
Absolutely.
GPS systems.
Absolutely.
Oh, okay.
I don't think maybe 10, I have 20 students at my lab, not enough.
Oh, okay. Okay.
Yeah, tons of work, tons of unknowns. Yep.
Thank you. I noticed that a lot of these interactions were sort of request response, like you say something and then it thinks and then it responds. Like, have you investigated some like way in which the dialogue could be tighter? Because let's say I'm talking right now and you are nodding. And when you are talking, I'm nodding. Like, did you investigate this kind of interaction?
Yeah. So you can fill in the hole. Yeah, the gap. Yes. So we have been thinking about it. It's just that again, there are more critical issues, so I couldn't really get to that point yet. Yes, you're right. Absolutely. Yeah, there are many ways that we can solve that kind of, at least to mimic it, so that people interacting with the avatar will feel as if that the avatar is going all the time. Yes.
Okay, I was thinking like mimicking is one thing, but the other thing is like having feedback from the avatar that it understands what I'm talking about as I'm talking about, like this kind of thing.
Sure.
It's on the shelf, right?
Yeah. So that could be another like gesture response or some ways to make it more natural, right?
Yeah, I see.
Actually, I could have also shown how avatar would react if I tell her something like scary or something, right? She would react slightly different. I'll show you, some other time.
Thank you.
Yeah. So now what I'm trying to say is that you see the whole world is now, there are many, many different opportunities, there are different problems, different challenges, right? Now that the loop is not completely all closed. New world.
Okay, so let's close the seminar at this point. And so thank you again. Yeah.
Thank you.
And a couple of quick housekeeping.